Hello everyone and welcome to lesson 8.3. This one's on solving logarithms and exponential equations. So utilizing the rules from 8.2 and some of the ideas about logarithms from 8.1, we're going to finally solve some equations. Okay? First thing here is there's going to be a few things we need to know. And that is conversion between logs, right? Something we've practiced in the last two lessons. For example, if log base 2 of x equals 7, this means that 2 to the 7th is x, yeah? It's a way of rewriting the log where the 2 is the base, the 7 is the exponent, x is the answer, okay? That's what this rule is here. We're going to be utilizing that, yes. The other is what's called the same base rule. This is a very basic rule. Basic rule. No, but it's pretty straightforward. If you said 2 to the x equals 2 to the 5th, then what is x? 5, right? X is 5, duh. So this is saying if b to the m is equal to b to the n, then m and n are equal. Yeah, then the exponents should be the same. Okay. We're going to do a few different techniques in this video. Some questions you can kind of use certain methods for. It just kind of depends on the problem. So the first is the most basic one, which is converting between exponential and log form. You've practiced solving for inverse functions already in the first lesson. That's kind of just that again. Number 2 is using properties to kind of change expressions, which might help us solve. And then what's called the same base rule, we're going to use that. And then we're going to see some old school factoring patterns to kind of have fun with those. And then lastly, taking the log of both sides. So this is going to be an interesting thing in one of the later examples, which uses the power rule to help solve logarithms. Okay, so again, this is just a variety of methods. Each of these examples is going to demonstrate a different method of solving. The first two examples are conversion between forms. So the idea is you want to isolate the expression, namely, if it's an exponential, you want to isolate the base and its power. If it's a logarithm, you want to isolate the logarithm. And then change forms using the rule. And I'm going to put the rule right here for reference. I don't like that O. Log base b of a equals x becomes b to the x equals a. Okay? All right. So we have 5 to the 3x plus 2 plus 5 is 6. First thing we're going to do, as I said, is isolate the exponential. So this exponential term needs to be alone. We will start by subtracting 5. Of course, 6 minus 5 is 1. Okay. Now that it is changed, right, I'm just going to invoke, hey, b to the x equals a becomes log base b of a equals x. So what is b in this case? B, the base, is 5. So this would just become log base 5 of, what's this equal to? 1. Okay, so of 1 equals the exponent, 3x plus 2. That's it. And so then this is just the equation we solve. Yeah? I'm going to say, oh, so 3x plus 2 is equal to log base 5 of 1. And we know log base 5 of 1, right? Because 5 to the power of 0 is 1. That means the exponent that would go on 5 is 0. So this just says that 3x plus 2 is 0. Thus, we subtract the 2, and then we divide by the 3, and we have our answer, negative 2/3. That is what x is. So it's really just conversion, right? You have an exponential, you isolate the exponential, you use the rule that's written in yellow to reverse it, right? To do the inverse function, to rewrite it in its inverted form. And then from there, you solve for x, okay? That's it for example 1. Example 2, similar thing. But now we're given a logarithm, so we're going to convert to exponential form. So similar few steps is we're going to start by isolating the logarithm. This will be achieved by subtracting the 2 from the 11 first to get 9 here. I don't like that equal sign or that 9. Equal, there we go. And then, of course, I have a coefficient of 3, so I'm going to divide by 3. Getting me 9 divided by 3 is 3. Now, it's logarithmic conversion, right? So it's log base b of a, which equals x, is going to become b to the x equals a. So what is the base for natural log? Natural log has base e. So we're going to use e to the power of, the exponent here would be the cube, and this is equal to x minus 1. So x minus 1 equals e cubed. Of course, just know that e cubed is a number. E is kind of like pi, remember? It's like 2.718. Not exactly, but, kind of. And so then I'm just going to add 1 to the e cubed. And there we go. That is my answer. My answer is x equals e cubed plus 1. Actually, I don't want to box that just yet. And you're done, really. But I have a few comments that I want to make. First of all, we can get a good decimal approximation by using a calculator, which we might do a little bit throughout the lesson. I'm going to do e cubed, plus 1. Oh, that was plus 4, silly. Plus 1. There we go. 21.0855. So I'm going to say that this is approximately 21.08. I'm going to round that 5 to a 6. Okay, that's it. This is my decimal approximation because, if you were using this for like a word problem or something and I don't know, someone wanted to know how many months till you have this payment, right? You wouldn't want to say, it will take e cubed plus 1 month. You'd be like, what? Rather, you'd say, oh, it would take about 21 months, boss, right? So, oh, okay, all right. Speak my language, nerd, right? E cubed plus 1, I don't know what that is, right? Anyway. Also, I had another comment about this, and that is your domain, okay? So something we haven't done yet in these 2 practice problems is actually check for extraneous solutions, okay? Now, we talked about in the past, one way to check for extraneous solutions is to take your answer, store it, and then plug it back in, right? Some of the solving practice you're going to do on quiz and test is not going to have calculator allowed, so how will you know if you're not going to check it by hand that way? Well, you just think about the domain of the function originally given. So, for example, in this first one, exponentials, right? 5 to the 3x plus 2. This has a domain of all real numbers. And why is that significant? Well, the problem with our previous functions like square root x and 1 over x, right, is those functions had a limited domain, right? Square root, you can't plug in negatives. 1 over x, you can't plug in 0, right, because those get you undefined or imaginary values. Thing about an exponential is an exponential looks like this, and it's graphed for all real numbers on the x-axis for the x domain. So whatever you get as an answer, as long as it's a real number, it's going to fall within your function's domain, and everything's going to work out just fine. So you don't have to worry about that too much. Where this might matter a little bit is the logarithmic functions. Because logarithms have particular domain. You see, natural log of x has a domain of x greater than 0. Okay? And this is because, right, if you think about the graph of natural log, we have an asymptote at 0, and it goes like this. Yeah? And then there's nothing in here. So you can't, if you said natural log of 0, that doesn't exist. If you said natural log of -1, that does not exist. So you can't get an argument that's negative or 0. So if it's 0 or less, bad, right? But we've changed the input sum. Natural log of x minus 1 is shifted right 1, so it has a domain where the argument x minus 1 needs to be more than 0, which tells us that x needs to be more than 1. Okay? Why does this matter? Well, whatever answer you get for the problem, the answer needs to be more than 1. Okay? If it's not, then it's not going to fit. For example, look, let's say, because we got x equals EQ plus 1, right? Let's say you got x equals 0.5, right? Well, 0.5 is not more than 1. And if you went here and you did natural log of 1/2 minus 1, that would get you natural log of -1/2, which would not exist. So that would cause an extraneous solution value, okay? So you don't have to plug it back in. If you have a calculator, you're welcome to verify it, but really you just need to think about its domain. And if you start with an exponential, you're chilling because it's just all real numbers, no worries. We don't care. If it's logarithmic, pay attention to the function transformations on the vertical asymptote. In other words, look at the inside of the log, set that more than 0, and solve, which is actually just like what we did in Unit 6 with natural domain of square root functions, right? As a quick aside, a quick example, right? If you said square root of 2x plus 4, how would you find the domain of this, right? You would say 2x plus 4 needs to be more than or equal to 0. And then you would subtract the 4, and then you would divide by 2, getting, hey, your domain needs to be more than or equal to -2, right? That's how we did that. Well, log is the same way, but you don't include 0. Yeah, 0 is not included because it's not touching. Okay, so that's just a comment about that. Okay, example 3. This says using the same base rule for exponentials. So again, what the same base rule says, let me do a really simple one for you. It's like super simple, okay? What is this? Okay. Let's say this, like 3 to the x plus 1 equals 9. This is like an extremely simple example. They're not the same base, right? 3 and 9 are different numbers. But 9 is special because 9 is 3 squared. So if you rewrote 9 as 3 squared, then what you get here is an equation showing the same base 3 and 3. Thus, since they're equal, they're exponents. You say, therefore, x plus 1 equals 2. The exponents are equal. And then you would just solve for x, and you would be done. Yeah? And so that's it. That's how the same base rule works. If it's not written in the same base, you change it to the same base to make it work. Okay? And so that is what we're going to do here. Though it's a little bit more complicated, right? The expression's a little bit more complex. So solving for x, I'm going to take all of these constants here, all of these numbers, and change the base. Sorry, I'm taking a yawn break right there. Change the base. So I look at the number 8, I look at the number 1 over 32, and I look at the number 4. Could these be rewritten as some number to a power, knowing that that number would be the same for all of them? Yeah? Well, 8, as it turns out, is 2 cubed. And 2 to the 5th is 32, so 2 to the -5th is 1 over 32. And so notice, so what I've done is on the left side, changed the 8 and the 1 over 32 into base 2, right? I'm going to do the same thing with the 4, rewriting 4 as 2 squared, which is then raised to the x plus 6. Okay, and now I am going to use the same base rule, but I'm going to clean this up to where it's just a base to a power equals to the same base to some power. So, first rule of exponents, again, yawning, sorry. Not bored, just tired. Actually, very excited. The first thing is right here, this is the exponential rule where you raise something to a power. So, for example, x squared cubed, right? This would be the rule where you multiply 2 times 3 to get 6. So what I'm going to do is this is times 2 to the negative 5 times x plus 1. And then it's the same situation here where it's 2 to the 2 times x plus 6 because the 2 squared is being raised to the x plus 6. Okay. Now you're going to do some distribution. Okay. You're going to say, okay, negative 5 will distribute to be negative 5x minus 5. And then this 2 will also distribute to get 2x plus 12. Now, the 2 cubed times the 2 to the negative 5x minus 5. Those are being multiplied. And when you say something like x squared times x to the 7th, you can combine through addition, right? Getting x to the 9th, 2 plus 7. So same situation here. This is 2 to the negative 5x minus 5 plus 3. Yeah, the 3 is going to get added with this expression. And of course, if we clean that up just a little bit, negative 5x, and then negative 5 plus 3 is negative 2. And so I have, don't forget my little 2 here. Sorry, let me clean him. 2x plus 12. 2x plus 12. Okay, so look at what we've sort of done here, though, is you've changed it so that they're both in the same base to 2, right? Thus, the conclusion here is you can say, oh, okay, look, then their powers are equal. So I'm going to say this. I'm going to write it nice and verbal. Since 2 to the negative 5x minus 2 equals 2 to the 2x plus 12, then the power negative 5x minus 2 equals 2x plus 12. And it's not because you got rid of the 2's, right? A lot of students say, what did you do? Did you just cancel the 2's? No. You didn't cancel the 2's. You just said, well, look, if 3 to the x was, 9, and 9 is 3 squared, then x is 2, right? So it's just a conclusion of saying, oh, the powers must be equal. That's the same base rule. If I subtract the 12 to the other side, I'm going to get negative 14. And if I add the 5x to the other side, I'm going to get 7x. This is going to leave me with x equals negative 2, which is our answer. For negative 14 over 7, it's negative 2. And so we are done. Yay! Woo! Yeah. And again, since this is an exponential, the domain's all real numbers. So we're relaxing, right? We're chilling. This is not anything to really check for extraneous. This is going to be fine. Our algebraic process is solid. Okay, that's the same base rule. All right. A little more juicy examples. So my favorites are examples 4, 5, and 6. All right. Here is example 4. This says, solve by taking the log of both sides. A quick note. This is the main method used in calculus. Yeah, this is the main method used in calculus, which is called solve by taking the log of both sides. So a comment about this rule before we actually do anything with it. the first thing is it uses the power rule, okay? It uses the power rule to take a log and take the power out. And if you remember, the power rule says if you have an exponent like this, you can drag the exponent out as a coefficient in front. So this method's going to work because if the unknown, the variable, is in the exponent, you're actually able to pull it out as a coefficient to get it out of the power, okay? Why is this used in calculus? Well, this is the common technique done prior to calculators, okay? With calculators, you can get answers like log base 5 of 1, like, okay, this one worked out, it was nice. But like if this said log base 5 of 2, then we would just do that. This method, it's another way of doing it, but it kind of plays a little bit nicer with other functions. Okay, so like if we weren't just doing exponentials and we had some other crazy stuff we were working with, this would be the method maybe used. So anyway, that's all that said. Let's see how this works. So the first thing is isolating your exponential just as you would normal. So this exponential equation, the 3 to the x minus 3 needs to be isolated. So first thing we're going to do is subtract the 2 to the other side. And then because they're both negative, we'll divide by a negative, getting me positive 3 to the x minus 3 equals positive 2. Now, here is what natural log, or here's what log of both sides means. When you take the log of both sides, you choose the log. Yeah, you choose. Okay, it can be any base you want. I, Mr. Spake, am going to choose natural log. Here's why. Natural log is associated with e, and e to the x is like one of the best functions to work with in calculus. I'm not going to tell you why, but it is. When you get to calculus, you will know what I mean, and you'll be like, oh my God, I remember Mr. Spake saying this. E to the x is like the coolest function ever in calculus because it does something that no other function is able to do. It has to do with what's called rate of change. Because of this, its inverse, natural log x, really plays well too with the things you do in calculus. And so it's a good idea maybe to just use natural log anyway because that's the standard one to use in calculus. Now, I say natural log. Does it have to be? No. You can use common log, which is actually very common to do. It's not uncommon. You can do log base 10 of this. You could choose the base to be like log base 3 or something. But if you were going to choose the base to be something that wasn't 10 or e, you may as well use the other method we've already talked about. Okay? So here's how this works. Okay. When you say take the log of both sides, there's a rule that says if log of x equals log of 2, then the implication is that x equals 2, right? Well, this actually works both ways. If log of x equals log of 2, then x equals 2. But if x equals 2, it is equivalent, or it is true, that log of x equals log of 2. And so what taking the log of both sides really means is applying the logarithm. So I'm going to use natural log here. Natural log of 3 to the x minus 3 equals natural log of 2. So this is not adding a log. You didn't say plus ln. You didn't multiply anything. You applied it. It was like a function, right? You know how we have f of x? It's kind of like if this was your thing and then you said f of this equals f of that, yeah? Which is essentially what you're doing. But it's with a logarithm, and I'm choosing natural log. Now, why do this? Well, because, as I just said, you can take the exponent now, right? I'm going to do this kind of thing. So that natural log of 3 to the x minus 3, this guy, the exponent x minus 3 can come out to the front, like so. And this removes it from the power. And then that's nice because now it's multiplied with natural log 3, which means the expression x minus 3 can be isolated by dividing both sides by ln 3. Thus, x can be solved by adding 3. And so this is my answer. Natural log 2 over natural log 3 plus 3. Which, as a decimal, right, ln 2 over ln 3, oops, not Desmos. If I say natural log 2 over natural log 3 plus 3, I get 3.63. Okay? And that's our answer. So this is roughly 3.63. Now, I want to compare methods, right? We had 3 to the x minus 3 equals 2. One of the earlier methods we talked about is converting the log, right? To say, oh, well, then that's log base 3 of 2 equals x minus 3. Oh, and then if you just add the 3, then this is x. And it's done in shorter steps. And I would say, yeah, sure, true. That's why this is a valid method. And you'll be tested on that method too. But if you go into the calculator and you say log base 3 of 2 plus 3, hey, look, you still get 3.63. So in a world where you have calculators, that method's fine, right? This method's valid. Like, it gets the same thing. It gets 3.63. It's less work, so whatever. But the reason I'm teaching you this, number one, it is advanced Algebra 2, so we're going through more advanced techniques than just the basics. Even though this works, assuming you're going on to higher math, this method's going to probably be the better method. Just trust me on this, yeah? Look, I majored in math. I went to grad school in math. I'm going to let you know. This is the method you're more often going to use, yeah? I don't know if I ever recall using that method in college, like ever. But I know that I did this all the time, yeah? So I'd like you to practice it within this unit. You will be tested on your ability to do this. There are some questions that'll tell you what base to use. Again, I chose ln, but you could have done the exact same thing with common log, right? And to show you in the calculator, if you did log of 2 and log of 3 plus 3, no, not minus, plus 3, you get the exact same decimal value, right? So it doesn't really matter. Like, the base did not matter there. They actually all come out to the same thing, which means if you have a calculator, it's going to work out no matter what. Okay, so that is that. Yay! I love this method, by the way. This is my favorite thing to do. Okay, example 5 and also example 6. This is where this gets a little bit more creative, yeah? A little more taxing. And I'll let you know, these next two questions are not super big items on quiz and test, okay? We're teaching it because we want to show you. I want you to see some cool stuff. It may pop up in the future or something. But really, it's just to expose you to different techniques and looking at math in a way that's different from how you would normally do things. Okay, so here's example 5. Solving using factoring patterns. This requires a lot of play. By play, I mean we're just gonna fiddle around. We're gonna say, I have an idea, right? There's me, and I'm thinking. I'm fiddling around. I'm thinking. Okay, here's what we do. By the way, this needs to say equals 0. I should have typed that. This says equals 0. Okay. What am I even looking at? 4 to the x minus 2 to the x plus 3 plus 15 is 0. 4 and 2 are different bases. 15 isn't even a base. It's not even an exponential expression. That thing we just talked about, taking natural log of both sides, ain't going to work. Just know. If you did natural log of this and natural log of this, well, guess what? That's useless, and that doesn't exist. So that is just terrible, right? This method is not going to work. What we're going to do is actually almost no logarithms in this. We're going to play. And here's how we're going to do this. 4 can be rewritten as 2 squared. This is true. Okay. And so I have this. Okay? 4 can be rewritten as 2 squared. Now, 2 to the x plus 3. You know the rule that says x squared times x cubed is x to the 5th? This is because that's x to the 2 plus 3. Okay, well, guess what? If you had x to the 2 plus 3, you could separate that as x squared times x cubed. So here's what I'm going to do. I'm going to do this. This is 2 squared to the x minus 2 to the x times 2 cubed, right? And by the way, 2 to the 2x, those multiply. That's 2 to the 2x. All right. Okay, we're getting somewhere. And then, of course, 2 cubed is 8. So I'm actually going to put that in front as if it's a coefficient on 2 to the x. Like this. Okay? And then the reason I didn't write 2 to the 2x right there. I'm actually going to do something a little bit different. So this came from the fact that 2 squared to the x is 2 times x, 2 to the 2 times x, right? Well, it is also true that 2 to the x squared is 2 to the 2x, right? These two things are equal. So I'm actually going to rewrite that as 2 to the x squared. Okay. And now I'm going to do something interesting. I'm going to say, let u be 2 to the x. What? Who was u? I said u is just a letter. I just said here's u. Then this 2 to the x is u squared. And this 2 to the x is also u. Thus, the equation, if I substitute u in place of 2 to the x, becomes u squared minus 8 times u plus 15 equals 0. Hey, wait a minute. That is a quadratic, and quadratics can sometimes be solved by factoring. What multiplies to get 15 adds to get negative 8, negative 5, and negative 3, of course. So then, this is u minus 5 times u minus 3, which equals 0. So then the roots of this would be u equals 5 and u equals 3. But wait, what is u again? We said, but u is 2 to the x. So then u to the 5 means 2 to the x equals 5. And u equals 3 means 2 to the x equals 3. Thus, these are simple exponentials to solve. And you could solve them one of two ways. The first way would be to just do simple logarithmic conversion. You would be done in one step. You could say, this is log base 2 of 5 equals x. And in this case, log base 2 of 3 equals x. That would be one way to do it. Another way would be to say, hey, 2 to the x equals 5. Then natural log of 2 to the x equals natural log 5. Thus, x natural log 2 equals natural log 5. Thus, x is natural log 5 over natural log 2. And just so you know, this and this are equal. They are equivalent. And if you did the same thing for the 3 term, you would get this. And that would give me my answer to the exponential. Yeah? Natural log 5 over natural log 2, which is the same as log base 2 of 5. If you don't believe me, Well, you should, because I'm your teacher. Just kidding. No, but if you don't, I'll totally verify. I'll go to the ends of the earth. There's natural log 2 of 5, and here's natural log of 5 over natural log 2. Boom, there it is. And by the way, let's say you take this bad boy, right? Take him, boop, store it for x, right? Store it in the calculator for x. Type in the original expression, 4 to the x, right? Was it minus 2 to the x plus 3? Plus 15? This should come out to 0. Okay, well, calculator pooped himself, but don't know if you know, but 7.105 e negative 15 is really close to 0. On a normal graphing calculator, a TI-84, this works and it says 0. I don't know what this guy's doing. He's probably rounding that decimal off, so whatever. But trust me, this figure, this e negative 15, this is basically 0. Okay, so it works. It's the answer, and there we go. Oh my gosh, isn't that method cool? Oh my gosh, right? You say, look, I took this weird exponential thing, rewrote it with the similar base, and then reinterpreted it like a quadratic, and then solved it like that. Fantastic. Oh my gosh, amazing. Okay, last example for the video. This is just getting creative using things you know. So this is like just some stuff from the past, putting all your skills together. So it says solve the logarithmic equation and give an exact value for x. So exact value means no approximating using a calculator. We'll show you that in a second. So here, let's try this out. So we got 2 logarithms. This is weird, right? 2 logarithms subtracted. Well, subtraction, there's a rule for that, right? First of all, I'm going to put the 2 as an exponent on that x right there. Okay, that's beautiful. Delicious. And then I say, well, hey, those are being subtracted. Don't forget my base 3. Those are being subtracted, which is going to be log division, right? So it's going to be log base 3 of x squared over x plus 1 using the quotient rule of logarithms. Well, now that you've sort of combined this into a single log, doing this lets you convert to exponential form, right? If log base b of a equals x, then b to the x equals a. Well, the base b is 3, the exponent is 0, and this equals x squared over x plus 1. But of course, 3 to the 0 is 1. So I got x squared over x plus 1. But then, hey, we need to solve for x. So let's multiply by x plus 1 on both sides. Then x squared is 1 times x plus 1, which is x plus 1. Now, hold on a second here. X squared equals x plus 1. This needs to be solved, right? This is a quadratic equation, which we usually do by factoring. So we got to use that zero product property, set this thing equal to 0, moving everything to one side. Problem is, -1 up here, -1 here. What multiplies to get -1, adds to get -1? Nothing. So what do? We say x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. There it is, our beautiful, lovely quadratic formula coming back into play since you can't factor, getting us 1 plus or minus. -1 squared is 1, minus 4 times -1 is like plus 4 over 2 here. So this is 1 plus or minus root 5 over 2. Amazing. Fantastic. And this is our answer. Except it's not, because we have to check for extraneous solutions, because we're actually solving a logarithmic equation, not an exponential, right? This one was exponential, domain all real numbers. This one was an exponential, domain all real numbers. So this logarithmic expression needs to be solved and check for extraneous because its domain is different. Now, log base 3 of x, that just input x says the domain is x more than 0. But then this one, x plus 1, that has to be more than 0 too. Sorry for yawning. X plus 1 has to be more than 0, which implies x needs to be more than -1. So between these two things, you need to make sure your answers are more than -1. You need to make sure your answers are more than 0. Well, if they're more than 0, they are more than -1. So really the thing that matters is that it's more than 0. So then if I look at my answer, 1 plus root 5 over 2, is this more than 0? Yes, because 1 is positive and root 5 is positive, so positive plus positive is positive over 0, that's fine. But 1 minus root 5 over 2, is this positive? No, because square root 5, right? Square root 4 is 2, and square root 4 is less than square root 5, which means root 5 is more than 2, which is more than 1. And so 1 minus root 5 is negative, right? Because root 5 is more than 1. And if you don't believe me, which you should because I'm your math teacher, I would say square root 5. Oh, it's 2.23, right? So, yeah. Turns out the minus is not part of the solution. Therefore, x is 1 plus root 5 over 2. One answer, not 2. It is not plus or minus. The minus is not part of it. 1 plus root 5 over 2. Ooh, that's a good one. Yeah. And so that kind of ties a lot of our stuff together, right? It's a good example. By the way, not all of these are going to follow this, right? This one was unique because you had two logarithms being subtracted, having to use the power rule, and then we ended up getting a quadratic, but it wasn't factorable, right? So you had to resort to quadratic formula. Sometimes it'll be factorable, and you can get it, and that's cool, and we're happy, right? We say, happy day, right? But, it's just going to depend on the problem. So, okay. Well, that is our 8.3 video. This was a little bit longer, but mainly for these last three methods, I think, the more complicated ones. Again, I want to reemphasize that examples 5 and examples 6, you're going to see these on the homework. They're not going to be major quiz or test items, so I wouldn't stress about it too much in terms of what you need to study for, though I still want you to get some practice with it, exposed to it, and use it a little bit, because who knows when this kind of stuff pops up again. And also, as always, it's fun, right? It's fun. These are fun problems, so why wouldn't we do fun things? We love fun things. Okay. I'm going to go do fun things now, which is called playing video games. And so I will sign off now. And say, have a good night or a good morning or a good afternoon or whenever you're watching this. And I'll see you in the next one.